Okay, we are talking about polymers. Now, we already looked at polymers before in topic 11. We talked about natural and synthetic polymers. A polymer is any type of material which is made by taking a bunch of small molecules that we usually refer to as monomers, and then by some process, heating, pressure, catalyst, we make long chains of molecules. They might often be tens of thousands of monomers long. That's what a polymer is, basically. We looked at two different types of polymer, addition polymers, which are made from any molecule that has a carbon-carbon double bond in, an alkene. Let's just put a chlorine there just to make it interesting. So that will be chloroethene. And then when I polymerize that, I break the carbon-carbon double bond. All the other bonds on the carbons stay the same. But then we get a new bond that sort of extends forwards and backwards to another repeating unit. And that's repeated n times, where n was the number of monomers we started with to make that polymer. So that's an addition polymer. Addition polymers are usually used to make sort of tough plastic items. Polychloroethene is also known as PVC. That's the stuff that's used to make drain pipes and ducting and tough plastic products, and also records, which seem to have made a strange comeback in the modern era. The V stands for vinyl, which is a word that's associated with the black plastic records. Right, sorry, I got distracted. Condensation polymers are made from two monomers. Let's use a bit of colour here. So let's have an acid group there, and then there's sort of a middle bit to the molecule, whatever that is. That's a molecule with two acid groups on either end, and then I'm going to add that to a molecule with two alcohol groups on either end. That COOH is the acid, OH is the alcohol. When we combine those, you remove water from the middle of the molecule, and then we condense the structures together. That's where it gets its name from. So if I start at this end with the acid end there, here we are, that's the acid bit, and then we have the alcohol bit there, and then the whole thing is repeated again n times. If I started with n of those and n of those. That will be a polyester, by the way, like Dacron. So polyesters are generally tough fabrics that we use to make things like my shirt and my jacket. Not my tie, that's made of silk, obviously. And some plastic products are made of condensation polymer. That's PET, or polyethylene terephthalate, which is actually a condensation polymer. Okay, so that's just a bit of a recap then. Properties of polymers depend on two things. So one of them, the most obvious one, is the type of monomer used. So if I make a plastic from chloroethene, I'm going to make polychloroethene. That'll have one set of properties. If I make it from just ethene, I'll make polyethene. I'll make a different kind of plastic. But the conditions under which the plastic is made, sorry, not plastic, polymer, also affect its properties. So for example, if I look at polyethene, so polyethene is made when I take some ethene monomers and do some clever chemistry things. There we go, that makes our polyethene, although usually that just gets contracted to polythene. So polythenes are very cheap and practical plastics used in many areas of our lives. There's actually two different forms. There's the low density form, or LDPE, low density polyethene, which is made, it's made under high pressure with a trace of oxygen. And low density polyethene, as the name suggests, it's got a low density, so there's that, but it's also relatively weak as a plastic, and it's got a very low melting point. The reason for that is, if you were to look at the individual polymer chains, you can imagine you'd see these sort of long chain polymers, but actually they end up as being quite branched, with sort of lots of random branches on, and that means that when one chain comes up against another chain, they can't get very close together. It's a bit like trying to put loads of coat hangers in a box. They just won't sort of stack very easily. So because they can't get close together, there are very weak intermolecular forces. I mean, intermolecular forces are always weak, but these are even weaker weak intermolecular forces, which are overcome easily, hence the low melting point. It was an important bit of history when a couple of guys, Ziegler and Natter, discovered a way of making high density polyethene, HDPE. The important thing they discovered was the catalyst. Ziegler, I think, became one of the richest men in the world as a result of this, so make a mental note. Find a catalyst, become rich. The reaction could be done at only 50 degrees, so that's barely higher than room temperature, and needed hardly any pressure. So unlike the high pressure for LDPE, the conditions were much more mild, easier to make, therefore cheaper. And it made a much stronger material with a higher melting point and obviously a higher density, and hence the name suggests. The reason it's got a higher density is the polymer chains are now largely straight, which means they can get up nice and close to one another, and the intermolecular forces are much stronger. Again, intermolecular forces are always weak when compared with covalent bonds, ionic bonds, or metallic bonds, but these intermolecular forces are stronger than those intermolecular forces. So the weak intermolecular forces would be stronger. Stronger than those ones, okay? Not stronger than, covalent bonds. Okay, so HDPE is pretty robust material. It's used in all kinds of things like milk bottles. That's your sort of standard supermarket plastic bottle, not the ones that arrive at your front door, if anybody still gets milk delivered to their house. You can just about see there the HDPE is printed on that, and a little recycled 2 is the plastic there. these two plastics are the most commonly recycled. They're both recycled on the Wirral, that's number one. That's number two. They're very easily turned into new plastic products, and so please don't put them in the bins. Okay, last little bit on. I'll just do this here. Last little bit on types of plastics, and you might have come across this in tech. The thermosoftening plastics and then thermosets. So thermosoftening plastics, what that means is when you heat it, it melts. Which is, again, most plastic products. If I heat up HDPE, don't have to heat it much above 100 degrees. The weakened molecular forces, yes, they're still weak. Weakened molecular forces are overcome by relatively not much energy. And the plastic melts. Okay. Thermosets, on the other hand, are polymers that don't melt readily when heated. So, whereas a thermosoftening plastic has polymer chains with weakened molecular forces between, a thermosetting plastic still has polymer chains, but this time has hard covalent bonds between the various chains. So we usually call these crosslinks. And they're made of strong covalent bonds. So if we try and heat the plastic up, it won't melt. So we think about something like rubber tyres. You don't want rubber tyres to melt. That would be a disaster. Tyres get very hot when you brake. If you braked hard for an accident and your tyres started to melt, your car would slide across the road and you'd go inevitably into a crash. So tyres instead, when they get very hot, they just start to break down. Imagine the guys on Top Gear doing donuts in a car, and the tyres are getting very hot. They start smoking. They might even catch fire, but they do not melt. And it only happens at much higher temperature. Okay.